Welcome back to our calculations for nuclear decay. So again, remember with all radioactive isotopes, we are going to be using first order integrated rate law equations for calculations. And again, the two main questions that we often want to solve for is how much of a nuclide is going to be left after a given amount of time. And that amount can be calculated as mass or percentages. And then we also, another variation would be to calculate how long it's going to take for a certain percentage to decay. As a good reintroduction calculation, our first one is if we're given the half-life of sodium-24, this is a radioisotope used in blood studies for medical purposes. That half-life is 906 minutes. We want to know the rate constant in inverse hours. First key thing to always pay attention to in these calculations is your units. Your rate constant and your time have to be in the same fundamental time unit so that they can cancel out. And then your amounts of substances, your initial and final, have to be in the same unit. So always pay attention to either what's requested or what's given. For this one, because we want to solve for the rate constant, we are simply going to use our modified half-life equation. So remember, we have 0.693 divided by half-life to solve for rate constant. But again, units. So one option is to convert your minutes to hours first. And in fact, that's what I'm going to do so that we don't have to worry about converting a unit that's in the denominator. That makes the setup, it's not hard. You just have to think more carefully about your setup for the conversion of those units. So I'm first going to convert my time into hours. For purposes of showing work, if you're ever asked in my class to show your work for this, I don't need to see this time conversion. I assume at this point that you know how to do that. I'm just showing it here to make sure that we're all on the same page, getting the same number. So that half-life in minutes converts to 15.1 hours. And again, this is our half-life. And so now I can simply plug that directly into my rate constant calculation. Notice with our setup, our hours is now in the denominator. That's going to give me the correct units that I want for my rate constant. Since this is all I'm being asked to solve for, I'm going to go ahead and round for sig figs now. So we have 3 sig figs in our half-life. That means I'm going to report 3 sig figs in my rate constant. So rate constant is going to end up being 0.0459 and inverse hours. So remember, you can write it as hours to the -1, and in fact, the 1 is optional. If you leave that out, it's implied. Or you could write it as 0.0459, that's a 5, and 1 over hour. So if that makes more sense to you, or if that's what the unit you want to use in the next step of a calculation, feel free. They're equivalent. For the rest of this video, we have these 3 problems that we're going to work through. So what I'm going to recommend is that you pause the video here, go through your setups, work these problems. Once you have a setup and a solution, come back. I'm going to work one problem on each slide. So go ahead and pause now and work through these. Okay, I'm going to assume you have setups and solutions by now. Again, notice we have similar examples that are listed in the textbook for extra practice. All right, our first question is asking if we ingest 75 milligrams of iodine 131, given a rate constant, we want to know how long. That means we're solving for time. How long would it take to decay to 12.5 milligrams? So really helpful hint here, remember that your initial amount, because we're always talking about reactants, your initial amount is always going to be the larger, your final amount is always going to be the smaller. So I don't want you to memorize that, but just remember that since we're talking about reactants always decrease over time. Since we already have a rate constant here, I don't need to use our half-life equation. I can simply use my first order equation and plug and chug. So we have this equation. Common mistake in this equation is omitting the negative sign as you go through. So it's often written in the equation because you have it on your equation sheet, but it is frequently omitted once you get into the calculation portion or start manipulating. All right, so again, we want to solve for time. And so that means if I were to just manipulate all of my variables, I'm going to have my final natural log of final over initial. To get time by itself, I need to divide both sides by the negative k, and that will give me t. And so plugging everything in here, I have natural log of, again, final is my smaller amount, 12.5 milligrams. My initial is my larger amount, 75.0 milligrams. I confirm that they're in the same unit, so that will cancel out. And then dividing by my negative k. So again, k is in inverse time, so inverse days. When I asked for how long, I didn't specify units up here. And so any units that you want to convert it to, if you want to leave it in days, totally fine. If, like in electrolysis, you want to convert it to something that's meaningful, if you get some astronomically large amount of seconds and you want to convert it so that you can grasp how long that is, that's totally fine. So as long as I don't specify units there, any equivalent unit is fine. All right, so again, common mistake is not using or not transferring that negative in front of the k. So if I didn't do that, I would end up getting a negative time. And what would that tell you? That it's impossible, right? Don't have a time machine. And so if you get an unreasonable number, if you get a negative time, or if you get a final amount that is larger than your initial, that's also because of the sign error with that negative. So those are the two things to look for in your final answer. Make sure your number makes sense. All right, so we are down to our final answer. We're going to round for sig figs. All of our given values went to 3. We are going to simplify life here. We are not going to use our sig figs with log rules. We're just going to go with regular multiplication, subtraction, or multiplication division. All right, since we had inverse days in the bottom, our unit comes out to be days. So it would take 20.8 days for this isotope to decay. All right, going on to our second example. Here we're working with gold 128, has a half-life, 2.7 days. It undergoes beta decay to become mercury 128. Interesting, not necessary for the problem. If we start with 5.6 milligrams of gold 128, we want to know what mass is left after 9.5 days. So we're solving for mass. That means we're solving for NT, our final, and we're given a mass to begin with. Different thing here is that because we're given half-life, our first step is to convert that half-life into our rate constant. Notice that the units of our half-life do match the amount of time we're given, so we don't need to convert units here. Since this is not a final answer, I'm going to keep extra digits. Again, remember, rate constants have inverse time, so 0.25667 inverse days. So now looking at our equation and plugging in what I have. Again, we're solving for final, so NT is my unknown, and N sub 0 is my initial. I have my rate constant. Using a little shortcut here, that rate constant goes in to K, and then we want to know after 9.5 days. So order of operations, I would first get a product of your K times time. Sorry, keep pressing the wrong buttons in my calculator. I would get the product here. You don't have to write it down, but just showing what that number is. 3 goes on forever. Our units cancel, right? Inverse days and days cancel out here. Now we have to figure out our next step in our order of operations. Realize if I want to get NT by itself, my next step, or eventually, I'm going to have to get rid of my natural log, right? I could separate this out as natural log of NT minus natural log of the 5.6. And I wrote the wrong unit here. Sorry, I wrote days. That is actually milligrams. Sorry about that. Right, so I could separate out my ratio of the natural log here, but that doesn't really help me because eventually I have to get rid of natural log. So I actually prefer to do it now. I'm going to take the E of both sides, so I get rid of that natural log. And so I'm going to have N sub T divided by my initial. And now I'm going to take E to my product. And again, this product over here has no units. Sorry about that. And so now we're down to a simple algebra problem. Our last step, of course, hopefully we recognize, is multiplying both sides by our 5.6 milligrams. And so that's how we end up with the unit of milligrams. So NT. Before we calculate, I want you to predict. Again, I'm solving for the final amount. So what do we know about that value? Hopefully you said that we know it should be less than the 5.6 milligrams, right? Our final is always going to be less than initial. And so when we calculate this out and round for sig figs, we have 2 sig figs in everything. And so we get 0.49 milligrams as our final amount. All right, hopefully you got all those right steps and solution for this problem. All right, the last one that we're going to work is a percentage problem. We're working with bismuth 214, extraneous information, doesn't really matter. Curious, doesn't matter. It decays by alpha emission, doesn't matter, unless I ask you to write that equation. Again, we have half-life given in minutes. We're asked to solve for time. We're not given a unit here, so I can keep my half-life in minutes. So again, our first step, because we're given half-life, is to convert that into a rate constant. So our K becomes 0.035178, keeping extra digits because it's an intermediate number. So there's my rate constant. Now we want to solve for time. So again, that means in this equation, we have to know both our initial and final, right? We just solved for K, we want to solve for T. Now we have to interpret our percentage phrasing. So we want to know how long does it take for 75% of bismuth 214 to decay? Right? So again, Remember, reactants always fall off. They're always decaying. So our initial is how much we start with. Since we're working with percentages, that's implied to be 100. What we need to figure out is what this is telling us. So if 75% of it is decaying, how much still remains? Hopefully, you came up with, no, I don't know where that jump came from. Sorry. Hopefully you figured out that we still have 25% left. So again, remember the final amount is telling me how much of my isotope still exists or is still present or hasn't decayed yet. So if 75% decays, 25% remains. So my final is going to be the 25. So our setup here is 25 over the 100 for our implied initial minus our negative of our K times T. So again, we want to solve for T. So we go through our calculations here. Again, remembering we have to have a positive value. So common mistake, if you got a negative time, it's because you forgot the negative in the equation. Never report a negative time, please. And so we see that our time here is going to be 39.4 minutes. All right, so we got our calculation. This is our correct answer. But did anybody catch that there's a second way to solve this? Maybe a faster way? So remember half-lives, right? A half-life is telling us how long it takes for a substance to decay by half. So for my substance, if I wanted to see how long it would take to go down to 50%, that would be one half-life. Remember that 50 to 25% is a second half-life. Pretend those units of time are the same. So we have our two half-lives that have to occur. So if I know the length of one half-life, but I know going from 100 down to 25 is two half-lives, another way to solve this is literally multiplying my half-life by 2. When I do that, guess what happens? It's amazing. All right, so there can be shorter ways to solve these. Look for those. It's not very common, but if you understand the concept of half-life, look for any value that goes down to a 50, a 25, a 12 and a half, 6.25, et cetera, et cetera. If you're solving for that amount, you don't have to go through all of this work to solve it. You can just figure out how many half-lives that is and then figure out the time that way. So pay attention to half-lives, pay attention to the information you're given. This, using the first order integrated rate law, will always work, but there sometimes are more efficient ways to solve. That concludes what we're going to cover for the nuclear chapter. If you're interested, the rest of the slides have some very interesting information, but those are for your information and for your personal knowledge later on.